So in the previous couple of videos, we've gotten used to this idea of vectors. These new objects that we can think about as arrows pointing in a given direction of a given length. And then we learned how to add together two of these vectors or to multiply one of these vectors by what's called a scalar to perform this stuff called scalar multiplication. What we did not learn is how to multiply together two vectors, because remember, scalar multiplication is the product of a vector and a scalar, not two vectors. Well, it turns out that multiplying together vectors is kind of complicated. When we talked about the addition of vectors and scalar multiplication of a vector, I sort of asked the rhetorical question of how would you like these to be defined? Because it turns out that everything works out just how you would like it to work out. Well, with multiplication of vectors, we're not so lucky. If we were taking the vector 2, 3 and the vector 4, 5 and we're multiplying them together, you might think we should just multiply component-wise. So this 2 times this 4 gives us this 8, and this 3 times this 5 gives us this 15. But it turns out that's not what we do. Not that you couldn't do that, it's just not useful to find the product of two vectors in this way. And you're like, all right, well, how do you do it? And the answer is, it depends. There's really two different ways that we can combine two vectors in kind of a multiplication-ish way. Those are called the dot product and the cross product. The cross product is something that you'll learn in a future class, but in this video I want to get into the dot product. Maybe we can learn it with an example. Suppose we have these two vectors u and v defined in their component form to be 2 root 3, 2 and 3 root 3, negative 3. For the visual learners, since the square root of 3 is like 1.7, 2 root 3 is roughly 3.5. So the vector 2 root 3, 2 could be depicted with this arrow. And since 3 root 3 is a little bit more than 5, the vector v with components 3 root 3 and negative 3 could be pictured with this green arrow. When I talk about the dot product of u and v, which we can write by putting a dot in between these two vectors u and v, really what I'm talking about is all sorts of complex. I'm going to take this vector u and project it onto the vector v. In other words, create a right triangle where u is one of the sides and part of v is the other side. That other side is the projection of this vector u onto the vector v. What I'm then going to do is figure out how long that new projection is and multiply that number by how long my vector v is. Whoa, wait, what? Why? Well, unfortunately, I can't really get into the why without getting into further linear algebra way beyond what we'd learn in this class. But maybe you'll trust me when I tell you that it'll be important to know how big the product of two numbers are, where those two numbers are the length of the vector v and the length of the projection of the vector u onto v. Let's start doing some calculations, and maybe you'll forget that you were ever interested in why we're doing this and be satisfied just figuring out what the dot product of these two vectors is. First, the length of u. Well, fortunately, we've already figured that out. We called it the magnitude of u and wrote it with this weird double absolute value symbol, and really just used our knowledge of polar coordinates to figure out that it's the square root of the x component of this vector squared plus the y component of this vector squared. For 2 root 3 squared, we recognize that the square root of 3 squared is just 3, and 2 squared is 4, and 4 times 3 is 12. And since 2 squared is 4, the magnitude of this vector u is just the square root of the sum of 12 and 4. That sum is 16, and that square root is 4. What I'm saying is that my vector u has magnitude of 4. The same calculation will work to figure out the magnitude of our vector v. We just take the square root of the sum of the squares of the components. So 3 root 3 squared is 9 times 3, or 27. And negative 3 squared is positive 9. So the magnitude of v is the square root of 27 plus 9, which is the square root of 36, which is just 6. And you're like, so the dot product is just 4 times 6 or 24? No, not quite. Remember, the dot product is not the product of the magnitudes of the two vectors. It's the product of the magnitude of the projection of one of the vectors onto the other one and the magnitude of that vector. In other words, it's this 6 times however long this little line in blue is. How long is this little line in blue? Well, the good news is we can figure that out using the trig we've learned. We have a right triangle here, and we know the length of the hypotenuse of that right triangle. So if we just knew the measure of this angle, we could use SOHCAHTOA to figure out the length of this little side in blue. Fortunately, we do know the angle between these two vectors because we can figure out the direction of the vector in blue and the direction of the vector in green by switching from rectangular to polar coordinates. If we wanted to know theta for this vector u, all we'd have to do is take the arctangent of the y component of this vector divided by the x component of this vector. In other words, the arctangent of 2 divided by 2 root 3. Well, I chose these numbers really carefully to make everything work out really nicely. 2 divided by 2 root 3 is just 1 divided by the square root of 3, which if we rationalize is the square root of 3 over 3. And you might remember from previously memorized values on your unit circle that the arctangent of the square root of 3 over 3 is just 30 degrees or pi over 6. Similarly, theta for this vector v is just the arctangent of its y component divided by its x component. Its y component is negative 3 and its x component is 3 root 3. So to figure out the direction of this vector v, we just take the arctangent of this quotient. You might notice that the same thing happens over here that happened over here, except now it's negative. So we get the arctangent of negative root 3 over 3 if we rationalize. And maybe you have memorized that the arctangent of negative root 3 over 3 is negative 30 degrees. So the angle pictured in blue is 30 degrees, and the angle pictured in green is negative 30 degrees when measured from our standard position. So the angle in red here is 60 degrees. Now that I know this angle, I can take advantage of SOHCAHTOA to figure out the length of this projection. The projection is the adjacent side relative to this angle t, and the magnitude of u, this 4, is the hypotenuse of this right triangle. So SOHCAHTOA tells me that it's the cosine of this angle t, the cosine of 60 degrees, that's equal to the adjacent side divided by the hypotenuse, or the length of the projection of u onto v divided by 4. Multiplying both sides of the equation by 4, we get that the length of this projection is just 4 times the cosine of 60 degrees, or 4 times 1/2, or 2. So this side length shown in blue here has length 2. Remembering that the definition of the dot product is that length times the length of the vector that it's projected onto, this 6, we get that the dot product of these vectors u and v is just 2 times 6, or 12. Wow. That was super hard to figure out. We had to do a lot of different calculations, convert between a lot of different forms, draw some pretty hard pictures. Dot products are the worst. It'd be really nice if there was like some shorthand way where we could just look at the components of u and v and immediately come up with this value of 12. Well, conveniently there is. With absolutely no idea of how this relates to this picture, what if we took this first component, 2 root 3, and we multiplied it by this first component, 3 root 3? After all, the dot product has something to do with multiplication, so it kind of makes sense to multiply. And you're like, but that can't possibly be the answer because that completely ignores the second components. Okay, what if we then added to that the product of the second components? So 2 times negative 3. I wonder what would end up happening. Let's see, 2 root 3 times 3 root 3. 2 times 3 is 6. Root 3 times root 3 is 3. 6 times 3, that's 18. 2 times negative 3, that's negative 6. So I got 18 plus negative 6. In other words, 18 minus 6. In other words, 12. Whoa, that's wild. Is that just because of the numbers you picked out? Nope. Can you explain to me the connection between this picture and this really easy formula? Nope. At least not without getting into some linear algebra that's way beyond the scope of this class. But the good news is if I'm not going to explain it, that means you don't have to worry about it a whole lot. Remember when I said that the vector 2, 3 multiplied by the vector 4, 5 is not the vector 8, 15? That's because you don't multiply vectors to begin with. You either take their dot product or their cross product, but neither the dot product nor the cross product is equal to 8, 15. But the dot product's pretty close. The dot product of 2, 3 and 4, 5 is this 8 plus this 15, which is 23. If you want a geometric interpretation of what's going on, you could say that the length of the projection of this vector onto this vector times the length of this vector is exactly 23. Why you'd care about something that seems so arbitrarily defined is beyond what we're going to talk about in this class, but the good news is there's a really shorthand way to figure out the product of those two lengths. All you got to do is add together the products of the components. So 2 times 4 plus 3 times 5. If you're the type that really likes a formula, if we have these two arbitrary vectors with components a, b, and c, d respectively, their dot product is just ac plus bd. A couple of comments here. The first one is really important. When we're figuring out the dot product of two vectors, our answer is not a vector, it's a scalar. Is there a way to multiply, loosely speaking, two vectors and get the answer to be a vector as opposed to a scalar? Yeah, kind of, but it deals with the cross product that we're not going to talk about in this class. The closest thing we'll do in this class to multiplying together two vectors is this idea of the dot product. And while the question involves two different vectors, the answer is just a single scalar. The second comment. From this formula, you can probably see pretty easily that a comma b dot c comma d is the exact same as c comma d dot a comma b, that the dot product of vectors is commutative. That just comes from the fact that addition and multiplication are both commutative. But it's surprising that our geometric interpretation is commutative. If I took the vector in green and instead projected that down to the vector in blue, and then multiplied together the length of that projection with the length of the vector in blue, it's pretty surprising that I'd end up with the exact same length that I got when I projected in the other direction and got 12 as my answer. But it does work out. The final comment that I want to make is you might be pretty frustrated that I spent so much time drawing this picture and talking about the dot product in terms of these projections, instead of just starting you out with this really easy formula that would allow you to come up with this same answer as 12. The reason why is one of the applications of the dot product is to find the angle in between the two vectors. In this case, we were able to figure out this 60 degrees because we were able to figure out the directions of this vector u and this vector v. Recall the angle in blue being 30 degrees and the angle in green being negative 30 degrees, which told us that the angle in red was 60 degrees. But wouldn't it be nice if we could figure out that 60 degrees without ever figuring out that this was 30 degrees and this was negative 30 degrees? Well, it turns out that you can. Recall that the dot product of u and v is just the length of the projection of this vector u onto this vector v. In other words, this short blue arrow here, maybe so I don't have to write the word projection over and over again, I'll call that vector, I don't know, w, times the length of this vector v. Using our vector notation, we can write that as u dot v equals the magnitude of w times the magnitude of v. Note that this dot is different from this dot. This dot is the dot product of these two different vectors. This dot means multiplication of this number and this number because the magnitude of vectors are just numbers, aka scalars. Anyway, supposing we didn't know this angle t pictured in red here, we could still relate together the length of u and the length of w with this value t. Focusing on this right triangle right here, we could say that the cosine of t is equal to the length of the side adjacent t, so the magnitude of the vector w, divided by the length of the hypotenuse, so the magnitude of the vector u. So if we wanted to rewrite this formula over here, but we didn't want the magnitude of the vector w in it, we could solve this for the magnitude of w by multiplying both sides of the equation by the magnitude of u. So the magnitude of w is just the magnitude of u times the cosine of t. With that substitution, u dot v becomes the magnitude of u times the magnitude of v times the cosine of t. So if what I really wanted to know was the angle in between these two vectors, I could solve this equation for the cosine of t by dividing all this junk over to the left side and get that the cosine of t is just equal to the dot product of these two vectors u and v divided by the product of the magnitude of the two vectors u and v. So t is just the arc cosine of that quotient. In fact, if you really liked formulas, you'd kind of take that as a formula, and that would allow you to answer questions like this pretty quickly. If we want to find the angle between these vectors 2 root 3, 2 and 3 root 3, negative 3, which we already know is 60 degrees from the work we did earlier, but if we wanted to find it without doing that work, we could just use this formula. First, we'd want to know the dot product of u and v, which is just the sum of the product of their first components, 2 root 3 times 3 root 3, which is 6 times 3 or 18, and the product of their second components, 2 times negative 3, which is negative 6. 18 plus negative 6 is just 12. Then we need to know how long is this vector u, in other words, what's the magnitude of u. That's just the square root of the sum of the square of its x and y components, which we saw earlier is just equal to 4. And finally, the magnitude of the vector v, which is just the square root of the sum of the squares of its x and y components. We saw earlier that this is just equal to 6. We now have the 3 different pieces that we need for our formula. We can plug those numbers in over here to figure out that t is the arc cosine of 12 divided by 4 times 6. 4 times 6 is 24, and 12 divided by 24 is just 1/2. So the answer, t, the angle in between these two vectors, is just the arc cosine of 1/2, which maybe you have memorized, is just equal to 60 degrees. The same 60 degrees that we found by adding up the directions of the two vectors u and v without figuring out the directions of either vector u or vector v. That's not the only use of the dot product, but that's the only application we'll see in our class. What I want you to see is there are ways to multiply together vectors, but maybe not the way you would expect. And one of those ways of multiplying vectors is what's called the dot product, and maybe surprisingly, the product of two vectors is not itself a vector, it's instead a scalar. And while that number, the dot product, is in itself useful for circumstances that we won't see in this class, one application that we do know enough to see is how we can use the dot product and this formula here to figure out the angle in between two vectors. That's all I got on the dot products. That's all I got on vectors. So I'll stop things here.